Looking at 2.2, this would be, I guess, what we'd consider day 4 now. And this is the last of the section 2.2. And it gets into using a derivative to determine the rate of change of like velocity and acceleration. So it will start out with this position function, which the position function can be written as s of t equals negative 1/2 g t squared minus v naught t plus s naught. Now this sub-zero, what is the sub-zero standing for? I bet you're asking yourself that question. And all of those just mean an initial quantity or the initial value. So for the s, which is our position function, it'll talk to us about the initial height of the object. So these will be word type problems, and often we can determine what the height is in the problem. The initial velocity, perhaps we're launching a rocket, so it'll start off with an initial velocity of a certain quantity. Sometimes an object is just dropped from above, and then its initial velocity would be 0 if it's just dropped because it's starting from rest. G in the formula stands for the acceleration due to gravity, and there are 2 different values that you will want to memorize for that. In English units, it's 32 feet per second squared, and in metric system, it's 9.8 meters per second squared. In the formula, you'll notice we have this negative going on, and that's going to account for the gravity, the force of gravity being a downward force. And so I could have written this as negative 32 feet per second squared and negative 9.8, but then I'd want to take off this negative and call it a positive. So one place or the other, we need to take account for excuse me, the fact that we have this downward acceleration. More definitions are coming your way here. Average velocity can be thought of, and let's just put average here, not s of t. Average velocity is equal to s of t sub 2 minus s of t sub 1 divided by t sub 2 minus t sub 1. This hopefully kind of looks very similar to a y2 minus a y1 over an x2 minus an x1. This really is our typical slope formula. And when I put my x value into the s function, I'm going to get out a y value. So that's why s of t sub 2 minus s of t sub 1 are really talking about y values. Or really it's the position at time 2 minus the position at time 1, which then rings through as a change of position over change of time. So change of position over change of time. No matter which way you look at it, it's a rate. Okay? Instantaneous velocity will be defined as taking the derivative of the position function. So it's the derivative of the position function, that s of t function. And quick way to write it, of course, is that way. Velocity can turn out to be negative, it could be positive, or it can be 0. If velocity is 0, we know our particle or object is at rest, meaning it's not moving. If it's negative, we have left movement, or it could be going down. There's the 2 options. If it's a positive, well, you guessed it, it's either moving right or it's moving upward. Speed is the absolute value of velocity, and we could write this as, S for speed. Speed is equal to the absolute value of velocity. Okay. Think of the speedometer in your car. When you read the speedometer in your car, you're getting a positive quantity, no matter if you're going forward or backwards. That's the idea of speed. So problem number 90 coming out of the textbook. I'm going to change this f into an s. Let's just call it a position function. S of t is equal to t squared minus 3. This interval here is including the endpoints, and what this really is talking about is we have some x values from 2 to 2.1. Okay, another interpretation of the interval notation, and then putting it into an equality statement. Average rate of change. Average rate of change, often abbreviated as AROC. It is the average velocity, and we just talked about it on the previous page. In order to calculate the average velocity, we are going to take s sub 2.1 minus s of 2 divided by 2.1 minus 2. I'm using my endpoints here to find my position when it finished. Here's its finishing position. Here was its starting position. And if I take and subtract these two, I get change of position, don't I? On the bottom, I have time 2 minus time 1. This gives me the change in time. And if I divide them, I'm going to get a rate. All right, so how do I get s of 2.1? Well, I calculate it, right? S of 2.1 is equal to, go to my original function up there, t squared minus 3. I have 2.1 squared minus 3 equals something, and s of 2 squared minus 3, well, that'd be 4 minus 3, so that's going to be a 1. If you want to, you could use your calculator. This will be 4.41 minus 3, has a difference of 1.41. Now, there's our s of 2.1. That was a 1.41 minus s of 2. We calculated to be 1. Divided by 2.1 minus 2 gives me 0.1. The difference will be 0.41 divided by 0.1, and that will come out to be 4.1. That will be our average velocity. The next item says calculate the instantaneous rate of change, and in order to get the instantaneous rate of change, we look for the velocity. And the velocity of a function is calculated by doing s prime of t, taking the position function and taking its first derivative, finding its first derivative. So s prime of t, coming back up here, I'd have 2t minus 0, so it is 2t. They ask us to calculate v of 2, and then also v of 2.1. v of 2 will be s prime of 2, and I go into my derivative, put in 2, where I saw t, I get 4. V of 2.1 will be s prime of 2.1, which is going to be 2 times 2.1, giving us 4.2. Next problem, number 91, is quite similar. We want to find the average rate of change. We're going to do that by looking at s of 2 minus s of 1 divided by 2 minus 1. Using my endpoints on the interval, we're going to calculate the slope of the function. And that will give us, let's do a little work off to the side here. S of 2 will be negative 1 over 2. Okay, it's negative 1/2. S of 1 is equal to negative 1 over x. I'm following this function here. Call this s if you want. Negative 1 over 1 gives us negative 1. So I have my two values, and I can bring them into my calculation here. S of 2 was negative 1/2 minus s of 1 was negative 1 divided by 2 minus 1, which is 1, gives me negative 1/2 plus 1 Final answer is 1/2. The average rate of change on the interval from 1 to 2 is 1/2. Instantaneous rate of change asks us to find the derivative, basically. So the derivative of the function, s of x is equal to -1 x to the -1 if we want to rewrite this function. Take the derivative, s prime of x is equal to -1, the power comes down, multiplies by the -1, and then I reduce the power by 1. It's the power rule, right? -1 times 1 is 1, and I get x to the -2. So therefore, s prime of x is equal to 1 over x squared. They ask us to find two different velocities. Velocity at 1 is equivalent to putting it into the first derivative. 1 over 1 squared is 1. Velocity at 2 is put it into the derivative that we just calculated, and I'd have 1 over 2 squared, making this 1/4. Now let's do some physical type objects that are dropping. If a billiard ball is dropped from a height of 100 feet, its height s at time t is given by the position function, and we're going to write our own position function, where s is measured in feet and t is measured in seconds. They want us to find the average velocity over the following interval. We have just this one, and then we're going to find the instantaneous velocity at time equals 1. And I know this needs to be rewritten, doesn't it? It's not spelled correctly. So let's go back and read the problem. We're dropping a billiard ball from 100 feet. 100 feet would be where it starts, correct? That would be our s naught. So s sub 0 is 100 feet in the air. Its height at time t is given by the position function. Now, this ball was just in somebody's hand and then dropped, so it started from rest. It would have started with a velocity of 0 feet per second because it started at rest. From that piece of information, or those two pieces of information, we can write out our own position function for this scenario. And I'd have -1/2. I'm going to use 32 for my gravity because we're working in feet, so we need the English version of gravity's acceleration. T squared would be an open value plus v naught. V naught started from rest, so it's a 0, plus s naught, it started at 100 feet, so there's its initial position. I'm going to simplify this position function. -1/2 times 32 is -16 t squared plus 100. Problem number 1 asks for the average rate of change. I can find that by going s of, we're on the interval from t being 1 to t being 2, so let's start at the end, the position at the end minus the position in the beginning, divided by the time that expired. So I'm going to have a 1 on the bottom. If you want to, let's just go calculate what s of 2 is. Let's put in 2 into our homemade position function there, -16, 2 squared plus 100. That makes 4 times -16 is -64 plus 100. We pick up 36. Also, we need s of 1. S of 1. Go back to our position function. -16 times 1 squared is 1 plus 100. 100 minus 16 is 84. So, substituting, s of 2 gets substituted with the value of 36. S of 1 gets substituted with the value of 84. And I need to subtract those two. 36 minus 84 would be negative, and it would be 48, right? 36 and 48 should add up to 84. There we go. All right. a negative value. What's up with that? Negative 48 feet per second would be our average velocity. Negative because it's going down. That makes sense. Good. We know we've probably done that problem correctly because of the negative. It indicates a direction for us. All right. The second thing it asks for the instantaneous velocity at 1. To get the instantaneous velocity, we take the derivative. So, you know what, I'm going to write v of t, the velocity for some time frame, is equal to s prime of t. Take the derivative, 2 comes down, I get negative 32t plus 0. So it's just negative 32t. And I want to evaluate this at time equals 1. So the velocity at 1 is equal to s prime of 1. Substitute 1 in, and we're talking negative 32 feet per second. The last problem is a person diving off a diving board or a platform. The platform is 32 feet in the air, just looking at the picture. So it says at time 0, a diver jumps from a platform diving board that is 32 feet above the water. I also know that he is jumping upward with a velocity of 16 feet per second. The position of the diver is given by, and I'll help you figure that out, where s is measured in feet and t is measured in seconds. When does the diver hit the water? What is the diver's velocity at impact? Well, in order to answer those two questions, we first must get our position function. So s of t is equal to negative 1/2 g. I'm coming over to this general position function. Negative 1/2. 32, because once again we're working in feet. 32 t squared plus initial velocity. It said he jumped upwards with a velocity of 16 feet per second. That is the initial velocity, so 16t, because I go v naught times t. His initial position was a diving platform that was 32 feet in the air, so we'll have plus 32. Simplifying out this position function, negative 1/2 times 32 is negative 16t squared plus 16t plus 32. Okay, let's hang on to that. Question A, when does the diver hit the water? Well, this is 32 feet in the air. This is 32 feet in the air. And then this would be how high? Well, it would be 0. So when he enters the water, we have 0. So I'm going to set that to be my ending position, s of ending, or s of t. So I can take this equation and say 0 is equal to negative 16t squared plus 16t plus 32. How do I solve a quadratic? Well, I could use the quadratic formula, I could graph it, look for the zeros, or we could factor it. And in this case, factoring is not going to be too bad. It has a GCF of negative 16, so let's factor that out. That'll give us a t squared, a minus t, and a minus 2. Mentally, double check. Make sure you didn't make any errors to check to see that it comes back out to that. Checks out, looks good. Now, in order to find the zeros, let's keep factoring. We did the GCF. Now this above us will actually factor into t minus 2 and a t plus 1. In order to get my zeros, I'm going to take each of these factors and set them equal to 0. T is equal to 2. Take this factor, equal it to 0. And t is equal to negative 1. But negative time doesn't make too much sense, so we will exclude that possibility. Oh, obviously then, he entered the water at time 2. Very good. Part B, what did Part B ask? What is the diver's velocity at impact? Well, I need to get to velocity, and in order to do that, I am going to, whoops, didn't mean to move that. Let me put it back. Um, let's move this over because we have to borrow some information off this. So, part B, velocity at impact. When did he actually strike the water? Well, we found that in part A, it took him 2 seconds to get to the water, right? 2 seconds to reach the water. So we need to find the velocity at 2. How do I get velocity function? Well, velocity function is the first derivative off of position. So if we take our position function, we'll have negative 32t plus 16. And I'm looking right here, taking in the derivative of that function. Now, s prime of 2, which would be equal to the velocity at 2, is going to be negative 32 times 2 plus 16. That makes negative 64 plus 16, which gives us negative 48 feet per second. And makes sense because it's negative. He was diving downward. Negative velocity is a downward motion. Okay, very good. Homework is this assignment, and it is 4 questions long. You can see 93 has 5 parts to it. Many of those questions are kind of similar to what we just went through with the diver or else with the billiard balls. So good luck with those.